Alright, so this is 37 and 3/9. This is two sides of a triangle have lengths 12 and 15. Okay. I was in Narnia there for a second. So 3/9. Two sides of a triangle. Where'd it go? Have lengths 12 and 15 meters. The angle between them is increasing at a rate of 2 degrees per minute. So whatever this angle is, let's call it theta. Did they tell me to call it something? No, good. So screw it. We'll call it theta. So if the angle is changing at a rate of 2 degrees per minute, what symbol do I use to represent that? It's the change in degrees. It's change in the angle per change in time. So what's that look like symbol-wise?
D theta over dt.
D theta dt. I like it. Cool. Where'd it go? How fast is the length of the third side? The third side, we'll call it C. Increasing when the angle between the sides is 60 degrees. So when the angle is 60 degrees, how fast is this side changing? So what would that be in symbols?
dc over dt.
dc dt. All right, let me stop there for a second. So several important things I just did. I don't remember this problem, so I just had to, this is how you take a problem. You draw the picture, right? They didn't say it was a right triangle. In fact, that angle keeps changing, so you never know. So it told me two sides and the angle between them. Okay, cool. I drew the picture. I got to represent what they tell me with symbols, so that when I get to my equation, I know what the hell to do with those things, right? Wherever I see d theta dt, I'm going to put a 2 now. You with me? And then in symbols, I wrote what they're asking me. The change in side of this third side, you can call it whatever they don't want you. I'll call it C. Right. Okay, so what's the relationship here then? Uh-oh. Oh, shit. This feels like it probably is something to do with what? This is not a right triangle all the time. Maybe sometimes it is.
Sine angle sine or something.
Something like that.
Yeah.
You have to bring all that into it. So it is side angle side. I don't know if you guys remember what that means. So remember, I don't know how you're taught this. Law of sines versus law of cosines.
Yeah.
When can you use law of sines? Where are my pre-calc people? Anybody took me for pre-calc?
So
When can you use law of sines? When you can actually make a complete ratio. Do you remember law of sines?
when we use cosines.
What's the law of sines?
Sine
A,
sine
B, C. Yeah, sine of, it doesn't matter which way you set it up, but sine of A over
sine
A equals sine of B over B, blah, blah, equals sine of C over C. So if you can't make a complete ratio, you can't use this, obviously. So do I have a complete ratio I can make?
No.
No, I don't have enough information.
Cosine.
So I can use law of cosines. So what's law of cosines? Law of cosines, maybe now you see why I call it C.
C squared.
It looks like Pythagorean theorem, but remember, it's more general. Pythagorean theorem is nice, it's cute, but I want something that works no matter what the hell that angle is, not just for 90-degree angles. So it's got a little adjustment for non-right angle triangles. Right?
So
Minus
2ab cosine.
So 2ab cosine C. I like it. In this case, C is what?
C.
Angle C is actually angle theta. That's what I called it, right?
Oh, and find the derivative.
So I really want you to see what did I just do? I summarized everything they told me. Now I've got to come up with a function, a formula that relates all my variables. I need a formula that relates this side, this side, this side, and this side. And that's the formula. That's the only formula I have. The law of cosines. Now I can take a derivative of this, and that's going to be related rates. Right? What a silly reason to use it as a title, because it's the main idea behind every damn thing in this section. Get an equation that relates all the variables in your problem. Take derivatives. Now you have an equation that relates the rates. Oh, I really want that to make sense. This is something you're supposed to know. If you don't know it, okay, you can look it up. You can find it out. It should spur a little bit of memory. Side, angle, side. I like that. You don't have to remember side, angle, side, or ASS, the evil one, right?
Yeah.
Or SSAs, what a lot of teachers call it. Do you guys see where to go from there?
Yeah.
And now I can take derivatives. But just to see, what would the derivative of this be? What am I taking into respect to? Derivative with respect to what?
Time.
Time. I like it because everything's with respect to time. So if I take d by dt of both sides, let's do this side. What happens here?
CC.
2c
GCDT.
dc dt. So I dc dt is what they're asking me for. Do I know c?
C.
Do I know c? I don't know c.
No. You have to.
But when theta is 60 degrees, I can figure out what c is from the original equation I had. So that should start to get familiar. Whenever you do these problems, very often you got to plug it back into the original to see what the value is. If it survives the differentiation, you got to know what the hell it is. Oh shit! All right. Well, so when theta is 60, that's when you plug it into the equation, and then you can see what actually little c dude is. Do you understand why you don't want to plug this in at the very beginning? Do you guys understand why? If you plug stuff in and then take derivatives, everything in the universe is going to have a slope of 0. Because if you plug stuff in, you get a constant. So when you take its derivative, you get 0. Well, that's not useful. So you want to figure out derivatives first, and then plug values in second, so that you don't just make everything in the universe 0. Right, that would be a very boring universe. Is that enough to get you guys started? I mean, you're basically halfway there already with this. So that's not enough? That's all I'm doing. All right, cool. Anything else from homework? No. Maybe.
We can do resistors. Simplify.
Let's see. Well, they give you the formula there. Yeah, so they give you the formula there. Sorry, I'm in. So 35, they give you. Have them all in the right place? Yeah. So you don't have to know any circuit physics, right? They give you the formula. If you have resistors connected in parallel, this is how it works to figure out the total resistance. How fast is the total resistance changing when R1 is 80 and R? So you just so this is a very direct problem. I love this problem. Let's do this. You guys do this problem right now. They tell you that R1 changing at a rate. I got an R there. At a rate of, where'd it go? 0.3 ohms per second. I think the ohm is one of the coolest little symbols ever. R2 is changing at a rate of 0.2 ohms per second. So I don't know if you know, but ohms is what you measure resistance in, right? How fast is R changing? How fast is it changing at a time when R1 is 80 ohms and R2 is 100 ohms?
So with respect to time?
Yeah, they pretty much give it away right there. See that?
Okay.
The units are stupid awesome here. They're stupid important. They're very nice. I know exactly what I'm taking derivative with respect to because the units tell me that. The rate of change is per second, so it must be derivative with respect to time. Do it, do it, do it. Do something. As always, if you're not sure, you can just draw me a picture. Make me feel like you're working on it. You can ask people near me. I don't know if that's going to help you. I like that. Should make derivatives easier. Now notice, I want to make sure you get it. I didn't put an equal sign there, did I? Because that would be incorrect. I said R1 is changing at a rate of, so what symbol would this actually be represented with? The 0.3. What symbol would he use?
dr1 over dt.
dr1 dt. That's the rate of change of r with respect to time. That's what that is. So that would be dr1 dt, that would be dr2 dt. R2. So here you have to have faith in the process. I have a formula that I didn't create myself, but they told me this is how it works. So I'm like, okay, book, I'll trust you. And this is how it works. So I've got a formula that relates all the parts that I'm interested in. The stuff that I don't know something about, the stuff that I know something about. Yes, sir.
Can we simplify the formula? Like, find the general...
LCD and do all that? Sure. You could if you want to. I don't feel like it. So when I take the derivative here, what do I get?
Negative r.
Yeah, the negative one comes down.
dr dt.
Dr, minus 1, minus 2.
Minus 2.
Dr dt.
dr dt equals, and then they're all the same, aren't they? Minus, I don't need a 1 there. Minus r1 negative 2, got dr dt, dr1 dt, minus r2 negative 2, dr2 dt. So I know R1, I know I'm interested in a time when R1 is 80, when R2 is 100. I know dr1 dt is 0.3, I know dr2 dt is 0.2. I'm trying to figure out what dr dt is, right? That's their question. How quickly is R changing? That's their question. So is there anything up there I don't know? I don't know what the hell R is, but I can figure out what R is. And I want R at a time when what? At this time, right? So I said this to somebody after last class. This is the snapshot that you're interested in. So the rate of change of R is constantly changing because it relates to these guys and the size of these guys. So at a time when this is true, that's the snapshot I want to take. I want to take a snapshot. So if my related rates equation, my derivative equation, if it requires me to know some value that I don't know, I can just go back to the original function and plug stuff in like we had to do on this last problem. So how do I figure out what R is at a time when R1 is 80 and R2 is 100? Plug it in. So I got 1 over R equals 1 over 80 plus 1 over 100. You get something? Somebody got that?
$8,000 over 180.
Okay, sure. So you can do, this would be 100 plus 80 over 8,000, and then you reciprocate it to get R by itself. Cool. That's the way I would do it real quick in my head. So it'll be 8,000 over 180, and then whatever the hell that is. So R would be 8,000 over 180. All right, so 800 over 18, so 400 over 9, whatever that. All right, let me stop there for a second. Are you guys cool with that? I mean, you should be, I don't care what the function looks like. If I give you everything except one letter, you should go, oh, thank God, this is easy shit. Just got to plug this stuff in and do it. Just do it. Nice. So, not every time. When would I not have to worry about it? If that wasn't a negative 1, would the R still be there? If it was just R, what's the derivative of R? dr dt. Would I care what the original R was? No. So if the variable disappears after you take a derivative, you don't care what the original value was. Somehow the rate doesn't depend on it. This one does. It depends on what the value is at a time when R1 is 8 and so forth. Right? So now I know R was 800 divided by 18.
Plug it in.
And now I've got everything. I'm not even going to finish this out. You just plug in the values. You know that and the negatives can all go away. Is that cool? If you want to. Now you just got to plug in that value for R, plug in that value for R1, plug in that value for R2, plug in that there, plug in that there. You got everything you need now. Right? So you set up the equation, or they give it to you, that relates everything. Take the derivative, so now you relate the rates. Again, title's a good choice on the title. And then you step back from the equation you got now and you say, is there anything I don't currently know? Right? And that's why it's so important to write the symbols for what they tell you so you know what you know. Okay, maybe. And now it's just plug and chug. Now it's just plug and chug. Is everybody cool with going from here to here? The level of differentiation was not high. So from here to here should be easy. Now, if you can see that is going there, they give me those, and I figured out what that is. That's beautiful. This is algebra. Plug the values in, solve for the thing you don't know, right? Let it be nice when they give you the formula, because making the formula is normally the hardest part, like we saw last time with the cone, right? Creating the formula very often is the hardest part. If they give you the formula, probably not going to be as crazy terrible. Notice how I say probably, because I cover my ass. Never know. Okay. Anything else from homework before we do some example problems? Okay, let's do this. Let me give you guys this here. And what I think I'll do is, yeah, all right. I want you guys to do as much as you can. And then we'll do this before we leave. We'll actually figure these out.